Thank you, Naren. Hello all, welcome to the webinar again, tackling the water, energy, land, livelihood nexus in Tamil Nadu. My name is Shiv Vembadi. I am a researcher here in the energy division at Oroville Consulting. In this presentation, we'll first highlight the issues in the different well sectors, water, energy, land, livelihood, and how they are deeply interconnected, and solving these issues needs them to be seen as a whole instead of separate components. And particularly, we'll see the nexus in the context of Tamil Nadu. Then we'll go to how solarization of agriculture has benefits for multiple stakeholders, including the electricity utility and thus the state, as well as the farmer. We'll see that in detail. And then we'll take a look at the schemes that are available from at the central level for the well nexus. And then we consider the approach that we have taken in our report of the same name for solving the well nexus. This approach provides integrated solution for well. And then Martin will continue with a virtual case study that we have done to quantify the benefits from such a holistic approach to the well nexus. And we'll also see how much benefits are there statewide before finally moving on to the financing models for this approach and what the policy recommendations would be for this approach. So we'll begin. In India, because of the water-intensive nature of the crops that are grown, like rice and cotton, as well as because of the very inefficient use of water, which we highlight in the report, how India is much inefficient compared to other agricultural nations like China. Because of these factors, agriculture alone accounts for 80% of the groundwater withdrawal in the country. And this overdrawal of groundwater is further exacerbated by the fact that the electricity supply to the agricultural connections is erratic, that leads to farmer keeping the pumps open all the time, consuming even more water. And all of this again leads to the fact that agriculture accounts for 20% of electricity consumption in the whole country. And along with the fact that the electricity supply to agriculture in different states is either free or subsidized, this becomes a big burden on the electricity utility and the state. As you will know, the DISCOMs across the country have lakhs of crores in debt burden, and this burden has, in fact, over the last 1 year, has increased even more sharply. And this is a huge financial burden. And in fact, the new government that came in, all of this, the agrarian distress, the water crisis, as well as the health of the electricity utilities, they are on the top of the agenda. In fact, in a Niti Aayog meeting in June, the government acknowledged the severity of all these issues as soon as they came in. Just to highlight one point, which more is the agrarian distress. This again goes along with the water crisis and the financial burden on the electricity utility. In 2017, Niti Aayog came out with a report which said the average farmer household income in India is 1.2 lakh rupees only. This is the annual income from the high input costs as well as the low price that the farmers get. And this obviously is a huge stress on the farming community. In Tamil Nadu specifically, recent statistics show that you have more than one farmer committing suicide per day. And in fact, in other states, the picture is even more grim, like Maharashtra, which has more than 8 farmer suicides per day, according to recent statistics. And the government has finally come to acknowledging the severity of all these interlinked issues, the well nexus. Particularly in the context of Tamil Nadu, well nexus in the context of Tamil Nadu, it is again very critical for development because agriculture employs 40% of the population in the state, and environmental factors and climate change only make it worse. Apart from longer than usual summer this year, we had the past 2 years had consecutive droughts, and which affect the livelihood of the farmers severely. And lastly, in the state, the electricity supply to agriculture is free, which again, as mentioned before, puts big stress on the water level, groundwater level, because of the over withdrawal. Just to put this in context, in Tamil Nadu, there are 21 lakh agricultural pumps with an aggregate connected load of 8.9 gigawatts. And this accounts for almost 1/3 of the total installed power capacity of all utilities in the state. So this, in fact, is a major contributor to the health of the DISCOM, apart from the fact that the water crisis is also part of this picture. Solarization of agriculture. The second component of well energy is the easier one to handle amongst the 4 sectors, and it provides benefits, multiple benefits, and one of the biggest benefit is reduction of the cost of, in case of Tamil Nadu, it will reduce significantly the cost of electricity supply to the agricultural sector. This we show through illustration here. On the left-hand side is the business as usual case, where you have the pump connected, drawing electricity from the grid, and from what we know from Tangetco, the electricity distribution utility, at present the average cost of supply in the state is 8.04 rupees, 8.04. And on the right-hand side of the illustration, what you see is solar PV deployed in the farm, and the pump consumes part of the energy requirements are met from the solar energy that's generated. And you also have a bidirectional meter along with it. The savings from deploying solar energy has 2 components, which I'll explain here. The first component comes from the self-consumption of the solar energy produced at the farm itself. So this offsets electricity consumption from the grid. And if, let's say, we assume the levelized cost of solar electricity generation as rupees 4.6 per unit, then that represents a saving of almost 43% over what the average cost of supply is. The second component of the savings is at certain points, the solar energy generated will be in excess of what's required by the pump, and that will be exported to the grid, and it will be sold by the utility to other consumer categories. And assuming cost of electricity generation as from solar as 4.60 and adding to it the distribution loss as well as overhead costs incurred by the utility, the cost of exported solar to other consumer categories comes to around 6.46, and still it represents savings of almost 20% over what the average cost of supply is. We have assumed, in the case of Tamil Nadu, in the context of free electricity supply to the sector, we assume that the solar plant in the farm is deployed, installed, and owned either by the utility or a third-party RESCO, because farmer wouldn't have the motivation to go with the capital expenditure. And therefore, the farmer would have to be given an incentive to maintain those panels. This incentive can be properly designed so that the farmer gets an extra revenue, as well as he's incentivized to maximize his consumption of solar energy, daytime consumption of solar energy, and reduce his dependence on the grid. This incentive we show how we have formulated the incentive. It can be, here it's given as solar energy production minus what the pump energy consumption is, minus what the energy import from the grid is. And then that is multiplied by a certain farmer incentive, which we have assumed at ₹1 per kilowatt hour to get to the incentive that the farmer gets. We take these example numbers from the virtual case study, which Martin will come to shortly, which is based on a 12 kilowatt plant in a 5-acre banana farm. And these numbers correspond to that. I apologize, there's a mistake in the number that's calculated here. This should be 6,807 kilo units and multiplied by the farmer incentive of ₹1 per kilowatt hour. So the farmer gets 6,872 rupees per month as farmer incentive in this example. The previous slide showed the savings that come from having solar at the farms. So that was at as of now, but given that the solar plants have a lifetime of 25 years, these savings will in fact increase over the lifetime of the panels. And this is what these graphs are here to show, assuming a 20-year lifetime. On the left-hand side, what we see is basically the cost of electricity from solar, which we have assumed at a 4.6 on a levelized basis, 4.6 per unit. The red line is what the cost of grid supply would be without any solar in the farm, and assuming it increases minimum at the inflation rate of 5%, you can see it increasing over the 20-year period. And then the brown line is what the solar cost of solar exported to other consumer categories would be the excess solar that gets exported. And you can see that the savings for the utility for solar consumed at point of production at the farm itself is basically the difference is the height of the red line. So the savings of electricity supplied to the farm, it will increase over the 20-year period. On the right-hand side, we have again taken the numbers from the case study that Martin will come to, and we have calculated what the total cost of electricity supply to the farm that we have, example farm that we have considered, would be over 20 years. And the orange line at the bottom shows with the export of solar energy as well as the avoided cost of grid import at the farm, what the cost of energy supply is. This also includes the farmer incentive, just to note. And we see that at the end of 20 years, there's a profit to the utility because the utility gets back more money than it is initially it has to put in for the solar plant at the farm. And the red line is what the business as usual case would be, assuming the inflation rate. The cost of electricity supply would keep on increasing to the farm. Coming to the schemes for Nexus, Nexus, which are there as of now. One of the main schemes is Kusum, which has been in news recently. It was launched, it was approved in February earlier this year by the government. And one of the components in Kusum is installation of 10 lakh grid connected pumps of up to 5 HP with an aggregate capacity of 7.5 gigawatts. And the excess power from these grid connected solar powered pumps would be sold back to the DISCOM. And there's a subsidy available as well from both the central and the state government. And the guidelines for the implementation of Kusum have been issued, and the implementation is still something to be seen and done. Apart from Kusum, we have the Pradhan Mantri Krishi Sinchai Yojana, which was approved in 2015 and with an outlay of 50,000 crores for the period of 2015 to 2019. Its main aim was bringing more land, cultivable land, under irrigation through utilizing more rainfall, as well as tapping more groundwater. And lastly, agricultural demand side management. Bureau of Energy Efficiency is undertaking this program to replace inefficient pumps with efficient pumps for better load side management, better load management of the farms. Coming to the approach we have taken in our report. So what's really needed is, we saw the different schemes that are available, but what's needed is something that combines all of this in a more integrated manner with each of these sector departments, the water, the energy and agriculture, coordinating together to implement the approach is what's really needed for the well nexus. And the approach we have taken has 3 components, starting with introduction of the solar plants at the farms, as explained, as we saw in some detail before. And then we replace the inefficient pumps with efficient pumps. And finally, deployment of advanced irrigation technologies. And in this scheme, in this overall approach, essentially energy is a pivot for implementation of the approach. It becomes the lever for the transformation. I'll hand it over to Martin. He will explain the analysis that we did to quantify the benefits from such an approach to the state.
Thank you, Shiv, and hello, everybody. Before going into the virtual case study itself, there is currently a lot of hype around Kusum. And what we are exploring is what could be an approach that various state governments, such as Tamil Nadu, could make that Kusum becomes a win-win for every stakeholder. That means the electricity utility, the farming community, and the residents of the states as large, if we look at water conservation and at greenhouse gas emission reduction. What we are presenting today is by and large based on the guidance of Kusum. However, we have not included any kind of subsidy in our financial analysis. So you may be aware that Kusum is suggesting 30% subsidy from the central government and 30% subsidy from the state government. The one point where we also differ from the Kusum as it is in the guidelines is that unlike the Ministry of Power that talks about the farmer investing into the solar plant, we are proposing that instead of the farmer, it could be a utility-driven program, or the investment could come by a renewable energy service company. And the quest that we really have, and Shiv already mentioned it, how do we turn a challenge when we talk about water crisis, farmer distress, and indebtedness for the utility into an opportunity, leveraging on grid-connected solar at the farm level. So I'll run you through a virtual case study. The assumption here is we have a 5-acre banana farm with a current pump of 7.5 HP. And we have assumed a load factor of the pump of 15%. So this farm consumes about 7,332 kilowatt hours of electricity per year for pump operation. This costs the state utility about 58,950 Indian rupees for the free cost of power supply. And the farmer income is assumed to be 5 lakhs per annum. Now we look at the interventions that Shiv has outlined. We talked about 3 interventions, and we are exploring a phased approach, starting with a grid-connected solar that is introduced, along with the farmer incentive, then adding energy-efficient pumps, and eventually then adding an advanced irrigation technology. So for the grid-connected solar, as mentioned, we propose that it may be driven by the utility or by a rescue. In this case, we assume a plant size of 12 kilowatt. We work with a levelized cost of solar of 4.6 Indian rupees per kilowatt hour. And we have the solar farmer incentive of 1 kilowatt hour that is calculated on the gross production of solar minus the consumption for the pump, minus the import from the grid. So what we also highlight here is the incentive is meant to do 2 things. A, it is meant to incentivize the farmer to reduce or to increase the efficiency of the pump, which also means to reduce the water consumption, because every liter of water that doesn't need to be pumped doesn't require electricity for pumping. And the second one is to incentivize the farmer to consume as much water during daytime hours when the solar system is producing electricity. Then for the efficient pumps, today most of the pumps are highly inefficient, so we have an efficiency rate of 25 to 30%. So introducing efficient pump sets, we assume it can result in a saving of up to 30% on the electricity consumption. Now, reducing the electricity consumption will increase the farmer incentive, which makes it very attractive for the farmer to consider this component. And similarly for the precision irrigation and the advanced irrigation. When we talk about precision irrigation, what does it mean? For us, this is an ICT-enabled tool that can remotely control the pump and it may take into account parameters like crop typology and soil typology and local climate information. The assumption here is that with the introduction of advanced irrigation technology, the crop yield can go up by up to 52%. And we will have substantial reduction in both water and in electricity consumption. Here we have assumed a 45%, which is rather conservative. We also assumed a reduction in input cost for two components. One is for fertilizer, and the second one is for labor, because the farmer is not required to operate the valves automatically in the field. He can control it from a mobile application. So business as usual, we take this 5-acre banana farm with the 7.5 HP pump. So what we have is an annual electricity consumption of 7,332 kilowatt hour. And as mentioned, a cost of supply to the DISCOM, to the electricity utility, of 58,950 rupees per annum. There is no cost savings to Tancheco, there is no water savings, and there is no increase in farmer income. Now what happens if we introduce now a grid-connected solar system? And there is a few assumptions underlining these figures that we present. So the first assumption is that the pump consumes about 50% from its electricity demand from the solar and the other 50% from the grid. Now, in this case, the electricity consumption per annum remains the same as compared to the business as usual. We still have a 7,332 kilowatt hours per year. However, the cost of supply, and this is in year one, decreases from the business as usual to now, with the solar, from 58,950 to 30,768. If we take now a 20-year horizon in percentages, this would result in cost savings to Tancheco and to the state government of about 86%. There is no water savings yet, but there is a small increase in farmer income of about 0.5%. So the farmer income here has been calculated taking into account that there will be a loss in agricultural income because some of the land will be taken up from the solar. And the 0.5% is on the annual net income of the farmer. So there's a marginal increase on farmer income on account of the farmer solar incentive. So if we can go to the next phase where we introduce efficient pumps in addition to the grid-connected solar, assuming a 35% saving on electricity consumption, the cost of supply comes down in year one to 5,132 kilowatt hours. That's in kilowatt hours, and the cost of supply in terms of rupees comes down from the initial business as usual 58,950 to 18,428. So that's a substantial reduction of cost of supply. If we again take a 20-year horizon, the savings to the utility are now a 108%. Water savings are not here yet. They will only come with the advanced irrigation technology. And the farmer income is now a 1.2% increase. So now let's look at the same. We have solar PV and we introduce an advanced irrigation technology, saving about 45% of electricity. What we have is that the energy consumption in year one reduces to 4,033 kilowatt hours. The same is with the cost of supply. It reduces to 12,258 rupees per annum. Savings for Tancheco or for the utility increase further. It goes to 119% over 20 years. There is now a 45% water savings on account of the advanced irrigation. And you see a very steep increase in farmer income of 65.9%. And this is primarily due that because advanced irrigation will result in substantial increase in the crop yield. Now finally, if we take all the three technologies, the grid-connected solar, the efficient pump and the advanced irrigation technology, how does it look? So the energy consumption is reduced further. Remember, we started with business as usual of 7,332. With the integrated approach, we bring it down to 2,823 kilowatt hours in year one. The cost of supply, instead of business as usual, where we have 58,000, we bring it down to a 5,471. What is really attractive is the savings to Danchenko, which are 130% on a 20-year time horizon. Water savings, we have a 45%, and there is a fairly high increase in farmer income, which is a 66.3%, which is very close to talking about doubling farmers' income. Now, this was just one farm. The question was also, and this is really an exploration, if this would be done with the 21 lakh of pump sets that we find in Tamil Nadu, what would be the cost and what would be the benefit for the various stakeholders? If we look at the bar chart on the left, and we have two bars here. The orange colored one is the net present cost of energy supply to the utility, and the gray bar is the net present value of the avoided cost to the utility. So we have business as usual, net present cost of energy supply in crores is more than 90,000 crore. And as we move on and introduce technology, the cost of supply goes down and the net present gains, so to say, increase substantially. So we have, introducing solar, we have avoided cost of 71%. Introducing solar along with efficient pumps, we save 100%. Then solar plus advanced irrigation technology results in a 117% saving. And eventually, if the integrated approach is being implemented, the savings would be in the range of a 130%, which means the utility would actually make a gain for the first time from the agriculture instead of a loss. The same if we talk about avoided energy demand from the grid. So avoided energy demand from the grid has a few benefits. It's not only financial benefits, but it also has technical benefits. It may also benefit in deferring investment into infrastructure because there is less demand on the grid. So if we look at it, again, I'm focusing primarily on the avoided demand in percentages. Introducing solar, we reduce about 50% demand from the grid. Having solar and efficient pumps, we have a 65% reduction. Solar and advanced irrigation technology results in a 72.5% reduction. And the integrated approach with all three technologies results in about 80% of energy demand from the grid. Similarly, if we look at the farmer, so what's in for the farmer? If we talk about a statewide application, solar alone, we have an increase in farmer income of about 0.2%. Solar and efficient pumps, we would increase the income by 0.9%. Where it becomes really interesting is once we introduce advanced irrigation technology, the income for the farmer increases to 69.8%. And with the integrated approach, we would have a farmer increase or an income in farmer increase of 70.2%. Similarly, if we are concerned about greenhouse gas emissions, of course, the different technologies will have benefits on CO2 emissions. So solar alone would reduce carbon emissions by 190%. Solar plus EE would result in a 221% reduction. Solar and advanced irrigation technology results in a 236% of carbon emission, and the integrated approach results in a quite an impressive reduction of a 253% of greenhouse gas emissions. Now the question is, how is it being financed and how can it be financed? So we have assumed in the report the following, that the solar system would be financed by either the utility or by an ESCO. the ESCO would be paid a certain tariff per kilowatt hour delivered. Here we have assumed a 4.6 rupees per kilowatt hour. The efficient pumps could be financed by the farmer as long as the farmer incentive is attractive enough for the farmer to get the fast payback. The advanced irrigation technology, we have also assumed it would be financed by the farmer, and it provides a fairly attractive payback. So what you see here in the table is just looking at the different stakeholders that could finance the various technologies and what would be their payback period if they were to invest into this technology. So one thing is clear, it is very unlikely that the farmer will invest into the solar because today he has free electricity supply. There would be no return or no rate of return and no financial return for the farmer if he were to invest into solar. So what could be done is, the first option is the farmer, instead of the farmer investing, an ESCO invests. The ESCO would have a payback period of 6 years without subsidy, and in case there is a capital subsidy of 60%, it would be a payback of 2.4 years, quite attractive. If the utility were to invest, the payback period would be 4.1 years without subsidy and a 1.7 years with capital subsidy. Looking at efficient pumps, the farmer would have a payback period of 6.8 years, which is primarily on the account of the farmer incentive. The ESCO, assuming that the ESCO would be paid 3 rupees for the avoided energy consumption on account of efficient pumps, would have a payback period of 6.9 years. However, if the utility were to invest into efficient pumps, they would have a fairly rapid payback of less than 1.5 years. Now, looking at the advanced irrigation technology, definitely the farmer has a very attractive payback period of less than a year without subsidy, and even less than half a year with subsidy. It appears that the ESCO investing into advanced irrigation technology will have a very long payback period, and it doesn't seem to be attractive. However, if the utility were to take up the investment, they would have a payback period of 5 years without subsidy, and potentially a payback period of less than 3 years with a subsidy. Now the final table is exploring how do we implement it, how is financing happening, and what are policy and regulatory changes that may be required to implement such a proposed integrated approach. Now you will see that for the implementation, the state electricity is pivotal in any technology application. For the main reasons also is they are the main beneficiaries. They will have most of the financial savings coming out from the technology application. So if we look at solar, if the utility is not going into the implementation themselves, they will be critical in identifying and aggregating the demand and the farmers. And they may, or a rescue may introduce and finance the grid-connected solar. What would be interesting is, of course, for the financing to avail the subsidies available by both the central government and the state government. What needs to happen on the regulatory front is it needs to have a dedicated gross feed-in for grid-connected solar systems at agricultural level. And the farmer incentive needs to be approved by either the DISCOM or by the regulator. Similarly, when we talk about efficient pumps, again, the utility will have a major role to play. If grid-connected solar is being introduced, it would make sense that the farmers are also informed about schemes for pumps and schemes for advanced irrigation technologies. Now, we have seen in the previous slide that the farmer has a fairly reasonable, good payback period if he were to invest into the pumps. Alternatively, the investment could come from the ESCO as long as there is subsidy provided for the capital investment. Talking about advanced irrigation, again, the utility is pivotal in rolling it out. This can be financed by the farmer because we have seen the payback is fairly attractive. Ideally, there would be a subsidy or a capital subsidy made available that includes advanced irrigation technology in the ongoing schemes for micro-irrigation. So just to wind it up, I guess the entire attempt here is to go back is how do we turn a challenge of free electricity supply to agriculture, extreme and radical and fast depletion of underground water table and the farmer distress into a potential opportunity. So we have seen is that combining grid-connected solar with efficient pumps and advanced irrigation technology would result into a win-win situation for everybody. That means the state government and the utility, the farmer by having an increase in farmer income and having a water security, and the state government and the citizens by reducing greenhouse gas emission and by an increase in water security. So we have arrived at the end of the presentation. I think Narayan will now take some of your questions and then get it across to us.
Thank you, Martin. And if there are any questions, could you please type them out in the little icon that you see below on the Q&A. I can forward those questions to the presenters. Are there any questions? Could you please, if there are any questions, please type them out in the Q&A box at the bottom of the screen. All right, if there aren't any questions, I would like to thank Martin and Shiv for this.
There is a question.
Oh, there is a question? I'm sorry. Okay, let's see that. Okay. This is from Vignesh to either you or Martin. Could you please explain a little bit more about advanced irrigation?
Yeah, so basically when we talk about advanced irrigation, we assume that micro irrigation is part of it, and by micro irrigation I mean drip irrigation or sprinklers. But the additional component that is added is an ITC-enabled tool that can switch on and off the pump automatically, that can operate the valves, that would work potentially with advanced weather forecasting technology, and you would irrigate automatically based on your certain soil conditions, your crop-specific irrigation, not even crop-specific, but specific for the life cycle of the crop. And one could eventually take into account evaporation rates to deliver the right amount of water at the right time for the right soil based on the crop and the crop life cycle. So typically that results in substantial water savings on top of a micro irrigation, but also increases the yield substantially. Would that answer your question, Vignesh?
Yes, Vignesh says yes. Do we have any other questions? Right. Okay, I think that's all the time we have for. So I would like to thank Martin and Shiv for those presentations, and thank you, Martin, for answering the questions that we had. As mentioned before, presentation, you can download the well report from the Affordable Consulting website. We'll also be sending out an email to all the registered participants containing a link to the recording of this webinar, as well as a form to collect your feedback. With that, I would like to thank you all for joining us and participating. We truly hope you found this webinar informative and will join us in our future webinars as well. Thank you.
Thank you, Narayan.